So in this lecture we will use Caret-Theodori theorem in order to construct the Lebesgue measure, which is the measure which extends to the sigma algebra generated by the intervals the concept of length. So remember that Caret-Theodori theorem tells you that if you have a measure which is defined on an algebra, you can extend it in a unique way to the sigma algebra generated by this algebra if the space has sigma finite measure. So what I will do today is I will represent by S the semi-algebra of the line R. So it's a subset of all subsets of R, in which S, it's composed of the empty set, the real line, the intervals of the form AB, where A is strictly smaller than B, and they are both real numbers, then the infinite intervals A infinity and minus infinity B, where again A is a real number and B is a real number, and I leave to you to check that S composed by all these intervals is a semi-algebra. We have defined mu in S to R plus union plus infinity as, well, mu of the empty set is 0, mu of R it's equal to plus infinity, mu of AB it's equal to B minus A, mu of A infinity it's equal to plus infinity, and mu of minus infinity B it's equal to plus infinity, and this holds for all B, and this for all A, and this for all B strictly bigger than A. So we have this function, and what I want to show is that this function is sigma additive, which means that if I have an element A in S and elements AJ in S, such that A it's equal to the countable disjoint union of AJ, then mu of A it's equal to the sum of mu AJ. So this is the goal of this lecture, to show that this function mu defined in this semi-algebra S is sigma additive. We have seen that mu, which is defined on a semi-algebra S, can be extended to the algebra generated by the semi-algebra S in a unique way. So I will represent by mu this extension. So mu is defined in the semi-algebra and mu is defined on the algebra. So remember, what we need to prove is that mu of A it's equal to the sum of mu AJ, but since mu it's an extension, in order to prove that, it's enough to show that nu of A it's equal to nu of AJ, where, recall, A and AJ are assumed to belong in S. The advantage in writing in this way, in introducing nu, is that nu is defined on a larger class than mu. So, for instance, I can always give sense to nu A B union C D, where say C it's strictly bigger than B. So this is well defined because the union of these two intervals is defined, it belongs to the algebra, so nu of this union is well defined, but nu of this expression is not well defined, and such type of sets will appear here. So this is the reason why I first rewrite this identity in terms of the function which is defined in the algebra. So this is the goal of this lecture, and what I claim is that there is an inequality which is always true. So to see that, well, I know that A it's equal to the joint union of AJ. Well, but this certainly contains the finite union. Now observe that this set belongs to the algebra because it's a finite union of elements of the algebra, so it belongs, but it might not belong to the semi-algebra. So this is why I introduced nu. So you have that A contains this set, therefore by monotonicity of the measure we have that nu of A it's greater or equal than nu of the union and now well, we will use that nu it's additive, so that which we have already seen. So this nu of this disjoint union it's equal to the sum of nu AJ. Now I can replace, if I want, nu by mu because this sets AJ belong to the semi-algebra, but I won't do that. I will now, from now on, always use nu. Since this inequality holds for any n, I can send n to plus infinity to obtain that nu of A is larger or equal than the sum for j greater or equal to 1 of mu of AJ. So this inequality always hold. We didn't use any special property of nu or of the set R. We just prove that this is always true if the sets A, J, D are disjoint and if A is equal to the union, provided nu is additive. So in order to prove our claim, what we really need to show is that nu of A is less than or equal to the sum of nu of AJ. And well, here we have many cases. So what, because A, it's remember, an element of the semi-algebra, so A can be a finite interval or an infinite interval. So I will first assume, that A it's equal to an interval A, B. So I will prove this inequality in the case in which A it's this interval. And so AJ is an element of the semi-algebra. It's contained in AB, so it must be of the form, it must be a finite interval. So I will present AJ by the interval AJ BJ. So with these two conventions, nu of A it's just the length of this interval, which is B minus A, and nu of AJ it's a BJ minus EJ. So I have to show that B minus A it's smaller or equal than BJ minus AJ, where aj it's given by the interval aj bj, and a it's equal to ab, and we have that a it's equal to the union of aj. So this is what we will prove now. So I just copied what we want to prove. A is the set AB, AJ is the set AJ, BJ. These are elements of the semi-algebra. A is assumed to be the countable union of AJ. And what we want to prove is that nu of A is smaller or equal than the sum of nu AJ, or this is equivalent, nu of A is just B minus A, and nu of AJ is just BJ minus AJ. So the proof, it's simple but relies on special topological properties of the line. So let's fix an epsilon positive, and what we know is that A, which is the interval AB, it's equal to the union of the intervals AJ, BJ. Right? So I just rewrote this identity, replacing A and AJ by their definitions. So, well, but this set here clearly contains the set A plus epsilon B. So let's fix epsilon small enough for A plus epsilon to be smaller than B. It's clear that A plus B is contained in AB. On the other hand, the set AJ, BJ, this interval is certainly contained on the interval AJ, BJ plus epsilon divided by 2 to the power j. And as I increase this interval AJ, BJ to the interval AJ, BJ plus something, well, these intervals are not disjoint anymore, and therefore I do not have any more a disjoint union, but I have just a union. So it's clear that well, this union is contained in that one. And now I will use a topological property of the line. I have here a compact set, this interval A epsilon plus A plus epsilon B, which is contained in a countable union of open sets, of open intervals. And we know that if we have a compact which is covered by a countable union of open sets, we can obtain a finite covering of this set. So we know by this topological, and observe that here we are using delicate property, topological property of the line. Well, we know that it follows from this condition that A plus epsilon B, it's contained in some finite union, k going from 1 up to m, of A gk, B gk, plus epsilon divided by 2 to the power gk. Right? So here we use the fact that the compact, which is contained in a countable open covering, it's in fact contained in a finite open covering. Well, now I want to compute the length of these intervals, but the length are defined only for intervals which are open on the left and closed on the right. So I will again use that, well, this set certainly contains the set A plus epsilon B, and that this set is contained in the union from 1 to m of AJ k, BJ k plus epsilon divided by 2jk and closed on the right. Now, at this point, I have an element of the semi-algebra which is contained in unions of elements of the semi-algebra, therefore in a union of elements of the algebra. Therefore, I can use monotonicity to say that nu of A plus epsilon B is less or equal than nu of the union from k from 1 to m of A gk B gk plus epsilon to gk. And we know that the measure of a union is less than or equal to the sum of the measures. This is a subadditivity property of a function which is additive and defined on an algebra. So this is smaller or equal than k from 1 to m of nu A jk B jk plus epsilon to gk. And, well, at this point, we have exactly what we wanted, because let's rewrite the left-hand side. The measure of nu of this set is just the length of this interval, which is b minus epsilon, b minus a minus epsilon. And this is less or equal than the sum of the lengths of these intervals, and this length is certainly smaller or equal to the one in which I sum every interval. So let's write that in two steps. First, this is certainly by this inequality less than or equal to the sum from k from 1 to m of bj k minus e j k plus epsilon to gk. But this is also less or equal than the sum if I take every term which appears here. So the sum from j from 1 to infinity of bj minus ej plus epsilon 2 to the power j, which is equal to the sum of bj minus ej plus epsilon. So what did we prove? We proved that b minus a minus epsilon is smaller or equal than the sum of bj minus ej plus epsilon, and since this holds for any epsilon, we do obtain that b minus a is indeed smaller than bj minus aj, which is what we wanted to prove. And this concludes the proof of this inequality in the case in which a is a finite interval. So what we want to prove is that nu of a is smaller than nu of aj for all a in the semi-algebra, and we have proved that in the case in which a is equal to ab. So now let's use this result to extend it to the general case. So what we will do is the following. Let me define En as minus n. So En, it's a sequence of elements of the semi-algebra which increase to R. And, well, it's clear that A intersection En, for any A, so I fix an element of the semi-algebra, and what I claim is that A intersection En is an element of the semi-algebra, because En is an element of the semi-algebra which is closed by intersection, but also that this element of the semi-algebra is a finite interval. Well, and therefore we can apply what we just proved to that measure. And I also claim that nu of A, it's equal to the limit of nu of A intersection En. as n goes to infinity. And I leave it to you to check. In order to check this identity, well, there are A being an element of the semi-algebra can be either a finite interval, semi-infinite interval, the empty set, the whole line. So you can check that in all cases we do have this identity. So now I also claim that A intersection En it's equal to the countable disjoint union of AJ intersection En. And again, since AJ is an element of the semi-algebra, AJ intersection En it's an element of the semi-algebra, and therefore we are exactly under the conditions in which we proved this inequality. So from the first part of the proof, we know that nu of A intersection En it's equal to the sum of nu of AJ intersection En. And this is clearly less than or equal to the sum of nu of AJ. Right? So we proved that for any n, nu of A intersection En it's less than or equal than the sum of nu AJ. So it's clear that this limit it's also bounded by this quantity, and therefore that nu of A it's bounded by this quantity, and this is exactly what we wanted to prove. So with that we conclude the proof that nu it's sigma additive in the semi-algebra, and therefore that it's sigma additive in the algebra, as we have seen. This is very easy. And now we can use Carré-Theodori theorem in order to extend this function, which is given by the length of the interval, to a function which is sigma additive, and it's defined on the sigma algebra generated by the semi-algebra. And observe that in the case of the line, the set it's clearly sigma finite, so that the extension is unique. So again we can use En as the interval minus n. It's clear that R is equal to the union of En, and that nu of En, which is also nu of En, which is equal to 2n, is finite. Therefore, this function defined in the algebra is clearly sigma finite, and therefore, as we have seen in the proof of Carré-Theodori theorem, that the extension is unique. So this concludes the proof of the existence of a function which is sigma additive and which is defined on the sigma algebra generated by the intervals, and which for a fixed interval AB gives to this interval the value of its length.